Solving systems of equations by hand can quickly become confusing and time-consuming. But what if there was a simple algorithm that always works, no matter the size of the system? Hey, I'm Oliver, and in this video, we'll take a look at Gaussian elimination and its extended version, Gauss-Jordan elimination. These algorithms make systems of equations easy to solve, and they even let us calculate matrix inverses systematically. If you are just starting out with linear algebra, I suggest checking out my playlist on linear algebra basics before continuing with this video. In that playlist, I introduce these systems of equations which you may be familiar with and explain how these can be converted into matrix representation. Now, in this system of equations, we can see we have variables here, and the idea, or the way to solve this system of equations, is to find out what values for these variables fits. So we get the results on the right-hand side. Here you can see that I've marked specific parts of these equations. You can see the coefficients in blue, the variables in green, and the outputs on the right. Now, there are certain operations which you can apply on the system of equations which do not change the underlying information. One of these is the swap operator. The swap operator would just change the order of these. So for example, the second equation here can just be put into the third spot, and then this would still include the same information as before. Another operation is the multiplication, specifically with a non-zero number. Now this multiplication with this non-zero number, a scalar, would have to be on both sides. So if we multiply this side of the equation with 2, we have to multiply this side of the equation by 2 in order to have this equation hold. So this is what the outcome would look like. So this equation still contains the same information as this one up here, since on both sides we multiplied with this 2. Now our last operation is the addition. This means we can add two equations to each other, and it will still include the same information. So doing this addition of these two equations gives us this last equation down here. And this addition also works with multiplying. So, for example, first multiplying this entire equation by another number and then adding it to this first equation. And this is possible because we're combining these two operators in a single step. Now, from a previous video I made on matrices, you may remember that we can turn this representation into a matrix representation that looks like this, where we have a matrix A multiplied by a vector x equaling to this output vector b. And this stores the same information, but in a more compact way. Now, for Gaussian elimination, we condense this format further into the augmented matrix representation, which you can see here on the right-hand side. We don't have the vector for x, we only have our matrix A and our output b. And we also add this separator line here to show us which part is A and which part is B. Now in this augmented matrix, we can apply the same rules or the same operators as before. We can swap two equations, which would be represented by swapping two rows, for example these here. We can multiply one equation by a scalar, so for example multiplying this entire row by the same number. And we can add rows to each other. So this row, for example, and this row, and it would be equal to adding two equations. Now I'm quickly going to run you through this Gaussian elimination so you get an understanding of how it works. In each step, I'm going to note down which operations we apply in a single step. On the left-hand side, I'll write the matrix we start with, and on the right-hand side, what it looks like after we've done the operations. And down here, I will list which operations I did. The goal of Gaussian elimination is to turn our matrix into a staircase form, where all the numbers below this diagonal, so these numbers and this number, will be 0, and in our case we want the diagonals to be equal to 1. However, in some books this is not required for Gaussian elimination and only for Gauss-Jordan elimination. Now in the first step, I will eliminate these 2's down here and turn them into zeros by subtracting 2 times the first row from each of these. Because 2 times this row will mean we subtract 2 times 1 from this area and this area, so that these will turn into zeros. I will also update the rest of the row accordingly. you can see here we have a negative 5 because we have a 1 here originally, which gets inputted here, and then we subtract 2 times L1, so 2 times 3 and negative of that, so negative 6 plus 1 is equal to negative 5. The same, for example, down here for this negative 8, where we're in the third row, we take what's originally in the third row at that position, which is a 12, and then we subtract 2L1. So this 10 up here times negative 2 is negative 20, plus this 12, we get negative 8. Now this was our first step, and now we have these zeros down here. Next, we will multiply this row in order to get a 1 here. In this case, we multiply this row by negative 1/5. Moving on, we eliminate this negative 4 down here by multiplying this row by 4 and adding it to this third row here. This adds a 4 to this negative 4, giving us 0, and immediately also gives us a 1 here and a 0 here. Since we already have a 1 here, it means that we've reached the form we wanted to, which is this reverse staircase. This is the end of the Gaussian elimination algorithm. Using this result, we can read out our answer. If we remember what this representation means, the third column represents the numbers that are multiplied by c. So 1 times c is equal to 0, giving us the answer that c is equal to 0. Now we can use that result and plug it back in the second equation and then the result of that into the third equation in order to solve each of the variables. However, we can also just apply Gauss-Jordan elimination in order to bring it into a form where we can read the result out immediately. Now Gauss-Jordan elimination, starting on the left side here, requires us to eliminate these values here and this one here in order to get the similar staircase format, but just up here as well. So these numbers become 0. Now we start by using the third row and this one specifically to eliminate these values up here using these operations. Now in a last step to eliminate this 3 up here, we utilize the second row multiplied by negative 3 and added to this first row. This way, this 1 eliminates this 3 up here, and this 2 turns into negative 6, added to 10 becomes 4. So now this resulting matrix can tell us what each of the variables is equal to in our solution. As before, this 1 in the third column is a c and is equal to 0. This 1 in the second column is a b and equals to 2. And this 1 in the first column is a 1 and equals to 4. Now I want to note that this was just one example and is the ideal case where we have exactly one solution. However, these values can differ in a way which makes it so that there is either no solution or an infinite amount of solutions. And I'll show you some examples. Now, if instead of this 1 down here, we just have a 0, we in fact have no equation which includes a c, meaning that the value of c does not matter to keep these equations intact. For example, if we have a is equal to 1 and b is equal to 2, these two equations still hold. And whether we set c equal to 4 or 4 million does not have an impact on this last line here, as the c is always multiplied by 0. So in this case, we have an infinite number of solutions. Now in the last case, where we have no solutions, we can, for example, have a matrix that looks like this. And in fact, this last equation tells us 0 times a plus 0 times b plus 0 times c equals to 1. But we know that this part would have to equal to 0. But we also know that 0 is not equal to 1. So in fact, there are no numbers for a, b, and c which would solve all three of these equations. And that is important to realize when you apply this Gaussian elimination, that not in all cases you will get a single solution or a solution at all. But there is always these three cases: one solution, an infinite amount of solutions, or no solutions. Now, we can also use Gauss-Jordan elimination in order to calculate the inverse of a matrix. For example, this matrix A here. I need to note that not all matrices have inverses, But this method allows you to find out whether a number has an inverse, and if it does, what that inverse is. Now, all you have to do for a square matrix A, which would be of size n times n, so it has n rows and n columns, is you put it in this augmented matrix form, which I've shown before, and then on the right-hand side, instead of just having a vector, we have a matrix, which would be the inverse matrix. So this part of the matrix, the augmented matrix, would have n columns, and this side as well. So in total, 2n columns and n rows. If you try Gauss-Jordan elimination on this augmented matrix here, and this matrix A on the left side is invertible, then the result will be that in the output augmented matrix, on the left-hand side, you have the identity matrix, the same as before, and on the right-hand side, you will have your inverse matrix. That's one way to find the inverse matrix. But if you see that on the right-hand side you do not have this identity matrix, then it means that the matrix is not invertible. Now, if you're not exactly sure what this identity matrix is and what this inverse means, I suggest you check out my video on inverse matrices, where I also introduced the concept of the identity matrix. If you want to see how linear algebra powers modern AI, check out my introduction to neural networks. They build on the same matrix ideas we use here, but at a much bigger scale. And if this overview helped, consider subscribing so you don't miss future videos on maths and computer science. And as always, thanks for watching.